a large variety of different interesting states upon moderate pressure variations. So this is the kilobar, 10 kilobar, 20 kilobar regime. You can screen to wide ranges of this phase diagram. So as I said, in these systems, in the one I mentioned, the molecules pile up to form stacks. There's a small dimerization in these stacks, and given that we have this 2-to-1 stoichiometry, we have one charge carrier, one hole per two of these molecules. So we are in the quarter filled limit in this case, and the occurrence of charge order here over wide ranges in the phase diagram, this has been understood as the combined effect of a strong on-site Coulomb repulsion U plus a significant intersite interaction V. On the other hand, if we go to the, so to say, second generation of organic conductors, this BEDT TDF-based systems, and I show you here a phase diagram of these kappa type materials. In these systems, they tend to form two-dimensional structures. So planes, they arrange in planes, and in these systems, the organic molecules tend to form dimers. So two of these have a close face-to-face interaction, form dimers. And this is the reason why in this system they have mainly described within the strongly dimerized limit. So then the dimer is the relevant electronic entity. We have one hole per dimer, so we are in the half-filled limit. And Mott physics is expected. And in fact, what we find here is in this kappa type ET to X first order Mott metal insulator transition. And this is governed by a single parameter U, or U over bandwidth. Now what becomes clear if we look at these phase diagrams, these provide really very nice test grounds for studying correlated electrons under well-controlled conditions. And with this I mean there's no doping-related issues. These are stoichiometric materials which you just tune by applying moderate pressure. We don't have to worry about doping-induced disorder or whatever. And these systems allow to investigate quite fundamental aspects of correlation physics. And this is so the outline of my talk. So don't worry, I don't want to go through all these different materials which I showed you in the phase diagram. I will essentially focus on one single material. This is this, I've just showed you the phase diagram of which, this is this which we abbreviate as kappa chlorine material. And I will start off by discussing a fundamental aspect of Mott physics which we can access in this material by applying small hydrostatic pressure. And this is the question, what is the role of the lattice degrees of freedom in the Mott transition? And then I will discuss the very same material but release the pressure, so at ambient pressure, we just reduce the pressure by 200 bars, and then we made a very surprising observation, namely that there's a ferroelectric instability. And this is not at all expected in a system close to the Mott transition. And it's even multiferroic, but there are open issues, and I want to address briefly these open issues. And I come to a system which is a slightly modified version. You recognize there's also a chlorine here, but here this kappa NCS2 is slightly modified. But this is the passive part of this system. But nevertheless, it changes it, and we use this material as we think a proof of principle demonstration that this concept of ferroelectricity in this dimerized system is actually valid. And then having this in mind, I come back again to this chloride material and show you a result of some recent inelastic neutron scattering measurements where we found very large phonon anomalies which we think now shed some light on this issue on ferroelectricity in this system. So the first part, the fundamental aspect of the Mott transition in this system. So although Mott physics is of relevance for a wide class of correlated electron materials, you know, there are only a very limited number of materials where you can actually access the Mott transition experimentally. And one of the examples we have seen on Monday in Colin Boham's talk, the well-known example is vanadium-2O3, vanadium oxide doped with chromium. And I show you here an example. This is a 1% doped representative. You see here a first-order Mott metal insulator transition which terminates here in the second-order critical endpoint at around 450 Kelvin. And typical pressure scales in this system are kilobars, tens of kilobars. Compared to this, our organic material, this kappa chlorine material, energy scale is much reduced. Here, the second order critical endpoint is below 40 Kelvin, and typical pressure scales are only 200 bars. And the phase diagram is even richer, so besides the insulating anti-ferromagnetic ordered insulating state, we even have a superconducting instability. Now with such a material at hand, we can then address quite fundamental aspects of the Mott transition. And one aspect which has been discussed over the years quite intensively is what is actually, or is this picture which we have in mind when we discuss a Mott transition, is this actually adequate for describing real materials? And the picture we have in mind is visualized here. We have a rigid lattice, and on this lattice electrons are hopping. And the motion of the electrons is simply dictated by the competition of kinetic energy and Coulomb energy, and for the Coulomb energy we simply consider on-site Coulomb repulsion. Is this adequate for a real material? In other words, what is the role of the lattice degrees of freedom when this electron gas is immersed in a compressible lattice? Is the lattice simply witnessing what is going on in the electronic channel, or is it more? And we can already answer this question by just what I've shown you so far, by looking at the phase diagram, where I indicate to you that the Mott transition in the system is controlled by pressure. And what we are doing with pressure, we just squeeze the lattice. So the lattice apparently controls the Mott transition in the system, so it has to be of relevance. And related to this, one can ask, what are the universal properties of the Mott transition when we include lattice degrees of freedom? Now there is an argument which goes back to work by Castellani, Ranninger, and Kotlia, that there is an analogy between the Mott transition and the liquid gas transition. And the notion is that for the Mott insulating side, when we are at finite temperatures, we have a small number of excitations. An electron is excited to hop to the neighboring site, leaving behind a hole called holon and a doublon. But these are at very low densities. And if you go to the metallic side, then the density of these objects is much higher, and these objects move around, giving rise to metallic conductivity. And as for the liquid gas transition, where the order parameter is the density, it is argued that in this case, the density of these objects, so to say, mimic the role of an order parameter. And as it is a scalar, then the natural universality class would be Ising universality class. And I think there's consensus in the community that for a purely electronic system, Mott transition would fall in the Ising universality class. The role of the lattice degrees of freedom, this has been discussed by a number of researchers in the field, and I'm referring here to the work of Manuel Zacharias and Markus Gas. And what they argue is, here in the temperature pressure phase diagram, when you approach the Mott transition and you are sufficiently away from the Mott critical endpoint, let's say in this blue regime here, then the lattice plays only a perturbatively weak role. It modifies, or it perturbatively weakly couples to the critical electronic system. And if your observable would be the lattice response as a function of pressure tuning, so what you would expect is essentially what you would see for a normal metal slightly modified. This is a linear strain-stress relation. This is what we call Hooke's law of elasticity. However, when you come closer to the Mott transition and you enter this yellow regime, which is called the regime of critical elasticity, then this coupling becomes non-perturbatively strong. And as a result, an elastic modulus will vanish and the lattice gets soft, and what we would expect is a strongly non-linear strain-stress relation. Now, in addition, because of the long-range shear forces in the lattice, these local microscopic fluctuations would be suppressed, and instead of Ising criticality, what we would expect is mean field criticality. Now, to bring this to an experimental test, what has to do is to explore lattice effects, relative length changes, around the Mott transition under control of temperature and pressure. And this means for us, we have to combine high-resolution dilatometry with tunable helium gas pressure setup. And this we have developed over the years. Now let me first, this is again our target material, our copper chlorine material. We are now sitting here at ambient pressure. Phase diagram says, this has been determined mainly by conductivity measurements, that the critical pressure which we need is 235 bars only, and the critical point is at 37 Kelvin. Now this is how an actual crystal looks like. This is the crystal we grow in our laboratory by electrocrystallization technique. It's a beautiful crystal, 0.5 millimeter etch size, well-developed faces and edges. And this is the setup which we used. In principle, it's very simple. So what you have to do is use a capacitive dilatometer, where relative length changes transform into changes of the capacitor of this plate capacitor, which you can measure with a very high resolution. So this ends up in a resolution of 10 to the minus 10. And this is immersed in a helium gas pressure cell. And because of the size of this dilatometer, the pressure cell is actually of this size. It's a 3 kilogram copper barrel pressure cell, which is then connected via a capillary to some room temperature pressure reservoir. So this is actually how the dilatometer looks like. It's a 25 millimeter in diameter, and this is then inserted from below into the pressure cell, and here's the metallic sealing of this cell. And instead of using such a compressor, in the simplest case, what you can do is simply use a helium gas bottle. And German safety regulations allow to pressurize these bottles up to 300 bars. And as you know from the phase cam, this is sufficient for our experiment. So what we used in the following experiment was really based on this, using these helium gas bottles. And with this setup, you can do two different kinds of experiments. You can do a measurement at a constant pressure as a function of temperature, but also pressure sweeps at constant temperature. And it turns out that for this Mott business, the latter experiment is much more suitable. So here are the results. So we started here at 300 bars at 30 Kelvin and crossed upon decreasing the pressure the first order metal insulator transition. This is what we got. We see a slightly broadened jump-like increase of the sample length, indicating that we are crossing a first order transition, so sample length suddenly increases. And this is also consistent with the notion that on the metallic side, the bond is a little stronger than on the insulating side. So once the electrons becomes localized, bonds get weaker, the lattice expands. Now if you increase the temperature stepwise up to 36 Kelvin, you recognize that the jump size gets slightly reduced. The width of this transition, which we assign to the effect of some disorder in the system, remains the same. But there's still a jump here. And then when you further increase the temperature to above this critical point, you still see strong nonlinearities in the relative length change as a function of pressure. Even at 43 Kelvin, this is way above the Mott critical endpoint, you see a strong change in the slope of this curve as a function of pressure. You have to go to temperatures as high as 55 Kelvin before you recover a linear strain-stress relation in this system. Now this diagram already contains, let's say, the essential message, and this is replotted here, namely that what we observe are huge changes of the material's compressibility. Here are shown now data for the B-axis and the A-axis. The compressibility, this is the derivative of this data, relative length change versus pressure. And what you recognize, even at 43 Kelvin, this is 6 Kelvin above the critical endpoint, the compressibility along the B-axis changes by a factor of 2. And here it changes even sign from plus kappa A to minus 2 kappa A. So it's a 100% effect. So compressibility changes are of the order of the compressibility itself. So the observation which we made around the Mott critical endpoint are consistent with this concept of critical elasticity, that there is because of the strong coupling of the electrons to the compressible lattice, there are huge changes in the material's compressibility. The data suggests that there's really an intriguing cross-correlations between electronic and lattice degrees of freedom in this regime of critical elasticity, and maybe we can find some new functionalities when these two objects are so closely interacting with each other. And our scenario also implies that this is of relevance for any Mott transition which is amenable to pressure tuning. And this holds true for the whole series of organic materials, but also for a large variety of materials showing the Mott transition in the oxides, for instance. Okay, now this brings me to the second point. Now we're looking at the same material, but now releasing the pressure, studying this at ambient pressure. Now we are here in the phase diagram, and we became interested in this field some time ago, back to 2012, when we studied together with the Augsburg group the conductivity of this material. And what we found, this is consistent with what other people found, namely that conductivity decreases, and around 60 Kelvin there's a break in the slope in the conductivity. And I indicated this because this becomes relevant later in the talk. And this was known for some time, but then what we found is that here around 25 Kelvin, there's a drop in the conductivity, indicating some partial charge localization or a charge order, which interestingly coincides with the Néel transition of this system. We're now going along this path. And the surprise was even bigger when we looked for the dielectric properties, and this is shown here. What we found is that in the dielectric constant as a function of temperature, there's a large peak in the dielectric constant. The peak height decreases strongly upon changing the frequency of this experiment, but the position remains the same. And this is a typical sign of order-disorder type ferroelectricity, which interestingly now also coincides with the Néel transition. It's the same temperature, 25 Kelvin. So we have two ferroic order parameters. This is a multiferroic approach. It's worthwhile at this point to recall what has been found already in these one-dimensional, in the Fabre salts. So the observation of ferroelectricity in this material, this has been well known for a long time. This goes back to work by Mott and Monceau, when they studied these Fabre salts, these quasi one-dimensional salts, across the whole series. And what is shown here is the dielectric constant as a function of temperature for the whole series, and they found huge peaks in the dielectric constants, reaching value of 10 to the 5, 10 to the 6. And as exemplarily shown here for this ASF6 compound, this is accompanied by a drop here in the conductivity. And this has been assigned to a charge order transition in this system. And the notion is that at high temperatures, the charging of this molecule is homogeneous. It's half a whole on average per molecule. And when you cool below the charge order transition temperature, then you have a charge ordering or charge disproportionation. The charge alternates between charge rich and charge poor across the stack. And according to Vandenbrink and Chomsky, this provides a new route towards an electronic ferroelectricity when the system changes from a situation where you have a homogeneously charged molecular states into a situation where you have a charge disproportionation. You induce local electric dipoles, and once this breaks inversion symmetry, then you produce a macroscopic polarization. Now this is electronic ferroelectricity as opposed to classic displacive ferroelectricity, where, so say, the ions sitting in the driver's seat, and it's the motion of the ions which breaks inversion symmetry and induces ferroelectricity. And an example is the off-center motion of titanium and barium titanate. Now it's worthwhile to have a quick look back. What is the phenomenology in these Fabre salts? And I'd show you here an example. This is this ASF6 compound, measurements of the dielectric constant from Mott. They found a strong frequency dependence at the peak height, but the peak position is practically independent of frequency. If you plot the inverse of the dielectric constant as a function of temperature, you get a straight line indicating you have a Curie-Weiss-like temperature dependence. And this is the same phenomenology which we observe in our two-dimensional system. And this is typical for order-disorder type ferroelectricity, where you have preformed electric dipoles which fluctuate at high temperature and which becomes ordered upon cooling. Now it's fair to say that first indications of ferroelectricity in these two-dimensional systems were reported by Abdel-Jabbar back in 2010. And this is a material which has become famous because it is a spin-liquid candidate system. And what they found is a peak in the dielectric constant, not that high, it's reaching values of 10, but it's frequency dependent all the way down to lowest frequency. And there's no clear signature in the conductivity as well. And this is a clear sign of relaxer ferroelectricity, where you have clusters of ferroelectric order with some inhomogeneities. And the model which they came up with, and which has been discussed here in a number of theoretical work, is that these ferroelectric signatures come from intra-dimer degrees of freedom. So the notion was that at high temperature you have some fluctuating charge on the dimers, which corresponds to fluctuating dipoles. And once you have a static charge ordering setting in, then these dipoles becomes ordered. The problem with this, and this is the open issue which I want to address, the problem with this scenario, either for this material but also for our chlorine material, is that so far There's no spectroscopic evidence that this scenario is actually true, that we have a charge disproportionation. So what they do, this is Martin Dressel's group, they look in the infrared spectra and they cannot identify two differently charged species of the organic molecule. So within their resolution, which is about 0.05 elementary charge, they could not find or could not identify two differently charged species of the organic molecules. So this is the problem. Over the time now, the number of materials which show this dielectric anomalies is steadily growing. Now we have a long list of material, most of which show this relaxer type ferroelectric order, with one exception. This is our chlorine system, which shows order disorder type. The phenomenology which we found here is very similar to the phenomenology for the Fabry sols, where charge order was clearly proved to be the origin of ferroelectricity. But in our system, the charge order hasn't been found so far. But this now calls for a test case where we have a dimerized ET to X material where we can really demonstrate whether or not this concept works. And a material which is well suited for this, and this brings me to the third part, is this mercury-containing material, which we think provides such a proof of principle demonstration. So this system is shown here. We call it now kappa HC chlorine. It has also this kappa type structure where when you look from on top, the ET molecules have formed dimer. But according to Harald and Rosé, the degree of dimerization, the intra-dimer hopping matrix element, is about 2/3 of that in our chlorine material. So here the degree of dimerization is only of moderate strength. This material shows a metal insulator transition at 30 Kelvin, and this is the resistivity as a function of temperature. Resistivity increases by 5 to 6 orders of magnitude below 30 Kelvin. And now if you look at the optical conductivities, this is Natalia Dritschko's work here, what they found is at high temperature in this optical conductivity, a single mode, indicating that there's only one species of charged ET molecule. But then if you cool below this 30 Kelvin transition, then it splits up into two peaks. So you have two different species, and from the splitting of this peak, they can really quantify the degree of charge disproportionation. And they found it is plus minus 10% of an elementary charge. So here we have apparently a charge order, a kappa phase, a two-dimensional ET to X system, which shows a charge order transition. And now it was attempting to look for the dielectric properties, and this is shown here on two different crystals prepared. One is prepared by John and the other one in our laboratory. We see sharp peaks in the dielectric constant at the charge order transition temperature. The broken line indicates a Curie-Weiss-like temperature dependent. There's no significant frequency dependence below 1 megahertz. This is really a textbook ferroelectric transition, now in a 2D kappa-based ET to X material. If we plot the inverse of the data, what we see is a straight line here, a straight line below, but with completely different slope, strongly different slope. And this is a clear indication of a first order transition, which we also confirm by thermal expansion measurement. And this is confirmed by comparing the data with this canonical first order ferroelectric system, the silver sodium nitride system. So when we want to discuss these observations in terms of dimerized ET to X materials, we can parameterize the strengths of a dimerization by this ratio T1, the intradimer hopping, versus over T prime, the interdimer hopping. So when we are here on the right-hand side, the limit of weak or no dimerization, then charge order is expected. We have the quarter filling, charge order is expected, and a very good representative of this scenario are these theta phase materials where this ratio is of the order of 1. On the other hand, on the right-hand side, in the limit of strong dimerization, our kappa chlorine material, this ratio is 5. Mott physics is expected, and charge order as the origin of ferroelectricity has been debated. But now this mercury chlorine material, the ratio is 3. It just sits in between these two border cases. Here charge order is well developed, well established, and it's most likely the origin of the observed ferroelectric instability. So this provides, now means, a clear proof of principle demonstration for the relevance of these intradimer degrees of freedom for the ferroelectric signatures we observed in these ET2X materials.
So all three are insulating at higher temperatures?
No, they are at, this system is, so to say, it has an activated behavior in the resistive. It's not it's a bad metal at high temperatures. This is actually a metal at high temperatures. It undergoes this metal insulator transition, this charge order transition.
Only insulating
at low temperatures.
At low temperature?
At low temperature.
Where is the ferroelectric temperature relative to the metal insulator?
This is actually, this is the same. This is the same. This is the same. Actually, it's 30 Kelvin. So it changes from a metal to an insulator at 30 Kelvin, and this is accompanied by this ferroelectric order. It happens at 30 Kelvin. Now this brings me to the final part. Now back. So after having shown that a ferroelectric instability in this dimerized ET-based material can be really found and is real, I'm coming now back to some recent experiments we did back in our chloride material, where we studied by inelastic neutron scattering the phonons in this system. So what we did is an inelastic neutron scattering study on a deuterated version of this material. To get rid of the incoherent scattering of the protons, we have to deuterate the materials. And the idea of this, the underlying idea was the following. Provided that their intra-dimer charge degrees of freedom are relevant, then the question of whether or not a charges on the dimer should affect certain phonon modes more than others. And phonon modes which we are particularly strongly affected by the presence of charge are intra-dimer either breathing modes or shearing modes in the dimer. Now given that the scattering intensity is proportional to the square of the momentum transfer times the polarization vector of the phonon mode you are looking at, we have to go to large momentum transfer to make the scattering intensity large, and in ideal case, this momentum transfer should be parallel to the phonon mode we are interested in. And so this was the reason why we selected the 603 mode, which I'm now focusing on. Here we're to the experiment. We did experiment on two spectrometers, one triple axis spectrometers, one was at the ILL in France and the other was at the FRM2 in Germany, in Garching. In this case, we used two crystals with an overall mass of 7 milligrams, and in this case, it was a collection of 6 crystals with an overall mass of 9 milligrams. Here are results. Here's shown a constant Q scan at low energies below 12 millielectron volt. And what we found are four clear peaks at 2.6, 6, 8, and 11 millielectron volt, which we could clearly identify as due to optical phonons from the dispersion which we looked at. You recognize that the peak width is about 2.3 millielectron, which is distinctly larger than the energy resolution, which is a half a millielectron volt, which indicates that we have a finite lifetime in this system, which is inversely proportional to the damping. And the damping we could extract by fitting four harmonic oscillator, damped harmonic oscillator functions to this data. This is the solid red line. Now when you do the same experiment at 75 Kelvin, you recognize that these three peaks here stay at the same energy. Whereas the lowest lying peak, this one here, appears to be shifted towards lower energies. Apparently there's a strong renormalization going on for this low energy peak, indicating that the damping factor becomes of the order of the bare mode itself. Now if you further cool down the system to 35 Kelvin and 27 Kelvin, these are the data here, you recognize this is essentially the same behavior. However, if you cool down to 5 Kelvin, then the peak recovers. So apparently this phonon renormalization effect is strongly temperature dependent. Now this is plotted here, the damping factor as a function of temperature. So we have strong overdamped modes in a certain temperature window, indicating that there's a phonon anomaly. And this phonon anomaly can be visualized particularly clearly when you go back to the data and now do an experiment where we monitor the scattering intensity at the lowest energy of 1.5 millielectron volt. And do this as a function of temperature with very high temperature resolution. This is shown here. So what we have here is that the scattering intensity at 1.5 millielectron volt as a function of temperature, it shoots up here at around 60 Kelvin. Then the scattering intensity stays high, and then it becomes rapidly reduced again at around 25 Kelvin. So such a phonon anomaly is expected whenever in your system the phonons couple to some other mode in the system in a resonant way, that it matches in energy and momentum. So what we are looking for is another mode in the system which matches in energy and momentum. And then I like to recall that at 60 Kelvin, this was the temperature where the conductivity rapidly dropped, which I showed you in the beginning. This is the temperature where the electrons start to localize on the dimer side. And at 25 Kelvin, this is the temperature where we have the anti-ferromagnetic ordering and where also we do see our dielectric anomaly. So this result, in particular these clear signatures here as a function of temperature, indicate that these anomalies, the phonons anomaly, are due to fluctuating intra-dimer degrees of freedom. And the very fact that we do see the anomaly at an energy of 1.5 millielectron volt tells us that the mode to which these phonons couple should be of the same energy, namely between 1 and 2 millielectron volt. So this means that we have charge fluctuation on the system, on the dimers, with this excitation energies. So how does now this complies with our observation of a static dielectric order, namely the observation of this peak in the dielectric constant? So on the one hand, we have here fluctuating dimers with this energy, and here we observe something static. How does this go along? So the difference in these two experiments is that here we apply a finite electric field. So what we believe what is happening is that this system actually is very close, just on the brink of developing static order, but is still fluctuating, and it requires a field, apply a field from the outside to make this thing static, to develop ferroelectric order. Okay, now to complete this picture, what we actually would need is we have to identify the low-lying mode which we have measured. So what we need is phonon calculations, and these are actually underway, and Rosé and Sananda, they are doing calculations. But because of the large unit cell, this is really a challenging task. There are more than 700 phonon modes. But what we can do in between is we can refer to a material, this is this spin liquid material, which has a similar, though not identical, structure. And here phonon calculations already exist. And this is the work published here in Martin Dressel's paper. And when we look in this paper, we could really identify the lowest lying optical mode here is 3 millielectron volt. And this is a mode where this dimer moves as a whole. This is not what we are looking for. But actually there is a mode at 4 millielectron volt where the two molecules within the dimer, there's shear. So it's a shearing mode. So why is it not identical to the mode which we found experimentally? Well, there are, as I said, there are structural differences. And if you look at the structure here, the differences refer to two aspects. One is in this compound here, the molecules have this alternating stacking, which is absent here. And as a result of this, these molecules are loosely packed in the out-of-plane direction. And another important aspect is the anions. The anions here have this polymeric type, whereas here they form these two-dimensional, more rigid networks. So both of these aspects go in the direction that the spring constants, which we expect for these materials, are distinctly softer than the spring constants here. And these softer spring constants, the whole phonon spectrum should be renormalized in our chlorine material as compared to this spin liquid candidate system, and the energies should be shifted to lower energies. So this brings me now to the summary. I started by saying that these kappa type ET2X materials are very nice objects to study correlated electron materials coupled to a compressible lattice. And then I focused essentially on one example. This is this copper chloride material. And I showed you that at a very small pressure of 230 bar, this is what you have on the tip of your ball pen. This is the pressure of 200 or 300 bars. This system allows you to access the Mott transition. We found huge changes in the compressibility around the Mott transition, indicative of this scenario of critical elasticity, which implies a very strong coupling of electrons to the lattice degrees of freedom, and maybe very interesting functionalities we can derive from that. And then by releasing this pressure, we made this observation, the surprising observation of ferroelectric signatures and even multiferricity, which then, by means of neutron scattering experiment, were found to be accompanied by strong phonon renormalization effect, which we then used as a probe to understand what is the issue with this ferroelectricity and the absence of a splitted peak in the infrared spectra. And now we came up with this scenario that what we are dealing here with are fluctuating dipole, that this system is still fluctuating. It's just at the brink of developing static order, and it requires a static field to make this system a static ferroelectric. And with this, I'm finished. I'd like to thank you for the attention.